Hello everyone, my name is Eleni and I'll present our recent work called Beyond Deterministic Translation for Unsupervised Domain Adaptation. So, a very common problem when deploying deep learning models in real world applications is that unlabeled target data encountered at test time may have different distributions from source data encountered at training time. So, for instance, let's say that we want to exploit synthetically generated datasets that come with rich ground truth to train models and then have these models perform well in real unlabeled images with different appearance properties. So, the main problem is that a model trained to perform well on a certain task on source data will not generalize well on target domain data. So, unsupervised domain adaptation can be a potential solution to this problem, and the goal here is to accommodate the different statistics between the source and the target domain. Previous translation-based domain adaptation approaches rely on establishing a transformation between the two domains, often referred to as pixel space alignment, that bridges the differences in their statistics while preserving the semantics of the translated samples. This translation can then be used as a mechanism for generating supervision in the target domain based on ground truth originally available in the source domain. However, a major shortcoming of this approach is that it relies on the assumption that this translation is a deterministic function, mapping a single source image to a single target image. But recent works on the closely related problem on unsupervised image translation have highlighted that this is a strong assumption and is frequently violated in practice. For instance, a nighttime scene can have multiple daytime counterparts where originally invisible structures are revealed by the sun and also illuminated from different directions during the day. Our work relies on stochastic translation to generate diverse outputs conditioned on the same input. And as you can see here, the translation network can generate scenes illuminated differently as well as different cloud patterns, allowing us to capture more faithfully the range of scenes encountered in the target domain. So, let me briefly describe the stochastic translation. So what we do is that given a source image, we can disentangle it into a domain invariant content code and a domain specific style code. Then we can replace the source style code with a random style code, some from a normal distribution with zero mean and unit covariance. Combining the random style code and the content code allows us to pass content from the source image to its target counterparts. The uncertainty in the translation is captured by the domain-specific style encoding that is inherently uncertain given the source image. So, in this way, we have a distribution of translated images to train the target CNN, and this allows us to leverage both accurate translation and data accommodation for appearance variability. Further, we exploit stochasticity in the translation to generate robust pseudo-labels for the unlabeled target domain data that allows us to train more accurate target domain networks. Specifically, we use ensemble of a triplet of networks, two target domain networks trained with different degrees of stochasticity in the translation, and a source network. The first target network is trained using a distribution of translated images, as we mentioned earlier. We train a second target domain network. And here, based on the understanding that the stochasticity driving our translation mechanism can be seen as implementing appearance level data set augmentation in the target domain, we introduce a simple twist to the translation mechanism that allows us to train networks that operate in different regimes. For this, we scale by a constant the variance of the normal distribution used to sample the random style code. And this amounts to generating more diverse translations than those suggested by the image statistics of the target domain. And this allows us to train a target network that can handle a broad range of inputs. Now, having shown how stochastic translation from the source to the target domain can be used for pseudo-labeling, we turn to exploit stochastic translation from the target to the source domain, which is freely provided by the image translation network. In particular, we consider a complementary segmentation network that operates in the source domain and can be directly supervised from the labeled source dataset. This network can provide labels for the target domain images when these are translated from the target to the source domain. In our case, we have a whole distribution of translations for every image in the target domain. So we realize that we can exploit multiple samples to obtain a better estimate of the pseudo-labels. So here, a target image results in multiple source domain translations, which are processed by the source domain network, and the predictions are averaged to produce pseudo-labels for the target image. So let's see some quantitative results. We start with an apples-to-apples comparison that builds directly on Advent and a strong baseline that proposed in 2019. Here, the first two columns compare the originally published and now reproduced numbers respectively. The third column shows the substantial improvement attained by training the system of Advent using translated images obtained from the deterministic translation, and specifically Cyclican, and the fourth column reports our stochastic translation-based result. And here we observe a substantial improvement that can be attributed to the stochasticity in the translation. Here we see some comparison with state-of-the-art methods on GTA to Cityscapes benchmark. And here we present per class IOU and min IOU obtained using the ResNet backbone. And we observe that our method outperforms recent state-of-the-art methods. Here we have a similar comparison, but using a different benchmark. Specifically, we use the Cynthia to Cityscapes dataset. And again, we present per class IOU and min IOU, and we observe that we get a substantial improvement compared to previous methods. So here we present some qualitative results obtained using the GTA to Cityscapes benchmark. The first column shows the ground truth. The column in the middle shows the results obtained using our method, and the column on the right shows the results obtained using DPL. DPL is a recent pixel level domain adaptation method that relies on deterministic translation and ensembling. and we can see that our method gives better results. We also have more qualitative results and ablation studies in the supplementary material and the main paper, so you can have a look if you are interested. And thanks for watching.